Good afternoon, everyone. I thought I'd try a little project since I was playing with building a power supply the other day. I might try, properly trying to build a power supply based on this little 12 volt. This was an AC power supply, so there was no rectifier, no smoothing or anything on this that I pulled out of. You can see the Dremel scar for me cutting off the housing. But I thought I'd hook this up with a regulator and see if I could, on a breadboard, build a 12 volt power supply just based on the schematic that I used in the last one. So let me get some stuff together and get a breadboard out and we'll see what we can do. Just a little safety warning, I think, before I get started. I think that's warranted. Obviously, if it's plugged in, these are going to be live at 120 volts. These are going to be live. There's a center tap, which I don't think is being used. Yeah, it's been tied together here, but that's going to be live. Right, so anything on this side is going to be live at mains. On the output, we should see 12 volts AC. It will probably be higher than that. And that's what we're going to use for our experimentation. The output should be comparatively safe to handle. This was a UL listed transformer, so we can assume that this is double insulated inside here. Certainly there's adequate separation from this side to that side. The question is whether there's adequate separation to the core, but I'm sure it's relatively okay. Anyhow, let's start playing with this. So our first step here is to solder some leads onto the output so that we can play with this. I'm just waiting for, I'm using the butane soldering iron because I don't feel like waiting for the other one to heat up. It should be getting there. Hopefully I'm still in the shot. There we go. Oops. Okay. There we go. So we've got two leads soldered onto there, and they could go into one end of this. So those should have 12 volt AC on them once it's plugged in. We'll check that and then we'll work forward from there. So let me explain to you how things are hooked up. So this is now plugged in, so this side of this little transformer, I will keep my fingers away, put it into the shot a little bit, should be hot at 120 volts. We're not going to touch the primary side in this little experiment. The oscilloscope probe of the Handtech here is hooked up to, I'm using the top power rail here for what should be AC into the circuit. And I've also got some leads coming out to the meter side. So let's go into the meter. No voltage DC, that's not surprising. Let's go into AC volts. And we've got 8 volts. I thought this was a 12 volt power supply. It appears to be a 6 volt power supply, or something like that. So we've got, maybe it's supposed to be a 9 volt power supply. I don't know. I remembered it as 12 volts, and that's what I wrote on it. Oh well. All right, so we're starting with 8.5 volts on the secondary. And let's see what that waveform looks like if we switch to the scope. All right, well that's obviously not the right. Let's just hit auto and see if it gets it right. Not very fast. And there we go. And now, so we can see a sine wave. We'll go back into menu. We'll enable frequency. And if you can see, it's very tiny in the corner, but it says 60 hertz. Again, I can't really zoom in much, maybe a little bit. You might be able to read that now. That says 60 hertz, right? So we've got what you expect. We have the primary coming in at 120, and we have a 60 hertz sine wave. So we'll see what happens when we rectify it. Okay, so I will do that. And so the first step of building our circuit is going to be to build the rectifier. So I will zoom back out. I'm going to pause for a minute and acquire some diodes, and we'll set them up and see what we get from that. I will say that I'm going to be very careful to unplug this transformer every time I do this because I don't want to brush across the primary. Again, I'm not terribly concerned about the secondary because it's a properly UL listed isolated transformer. But don't, play with this kind of stuff at your own risk, right? Okay, back in a moment. So I have everything unplugged. I have the cord over here to my left where I can see it. I don't want to have it on the ground. I'm going to zoom in for a second just to remind everyone what a rectifier looks like, a full bridge rectifier as it were. So we have the, again, apologies for the terrible drawing, but we have the AC coming in at the top, and we have the diodes pointing in the same direction on each side. So the diodes, if you want, point towards the plus and away from the minus. So what is that going to look like on our breadboard here? We'll zoom out a little bit so we can see that. So I have 4 diodes. These should be 4N something. Yeah. Sorry, 7N something. Yeah. What is that? Yeah, 4N 07. Yeah, 007, something like that. Anyway, it doesn't really matter. All right, so we're going to take this AC, and I'll maybe continue using yellow for the AC just so we can see what it is. And so let's build our rectifier. So I'm going to try to build it so it looks as much like that as possible, just to be neat. So we'll run one AC line. This is coming off the top one here to there. And then we'll run a diode out facing this way. And a diode facing that way. Okay. So then we'll run out of case I've for the other side. We'll do the same thing. So we'll run from here to here, keeping in mind that the tracks are split by the center of the breadboard if you're not used to working with the breadboard. Run that over there. So that's the other side of our AC coming in. And we'll run one diode like this. And that should have the positive coming out. We'll put that over here to the positive. Then we'll run the other diode facing the same way, like this, to there. And then out of that side, do I have, I'll use a blue one. That should be negative. So what we should have out of that is unsmoothed. I'll move these over here. is unsmoothed DC. So we'll just hook our test leads up here, the way around. This doesn't matter. Okay, so let's pull the scope back into the image. Zoom out a little bit. And I'm going to plug this in and come back. So now we have our diode bridge in, and it's producing DC. So in our little corner here, I don't know if you can see it, I've got everything on top. Just a moment. We have our little full bridge rectifier, our rectifier there, made out of 4 diodes. We have, that's coming in off the secondary of the transformer, which is just out of the shot over here in the corner. That is plugged in now, and it's giving an average DC voltage of 7 volts. That's just an average voltage. If we go into the scope, we can see what's actually going on. So I'm going to try to zoom in this time because I want to show you what's going on. And okay, there. I'm not reflecting a light. We can zoom into the scope. I can actually get this plugged connected to the computer, but it's too much of a pain. Okay, so we'll have wiggle vision. So what we're seeing is if you look at the frequency, we've got a frequency of 120 hertz. So because we're seeing both halves of the sine wave, it's double the frequency of the line current, which is 60 hertz, right? So that dips below the 0 point, which is, well, represented by the 0 point line on the scope right now. Okay, so this is unsmoothed, unregulated DC, created by the rectifier and a transformer. We can smooth it by putting a capacitor on it. Let's make sure. So I will do that right now. If we look over here, we can look at our DC power rails. This is our AC power rail. And I'll zoom out again. We can look at our DC power rail, and we can look at our AC power rail. And can we do this without having, okay, we'll do it like that, and we'll zoom out a bit more. I'm just trying to get reflections off of the scope screen. So look at the scope screen when I plug in. I'll make sure I do it the right way around. I will plug in an electrolytic capacitor just across the what I'm calling the DC power rail here. So look at the scope screen. Boom. Did you see that? So look at this again. I'm going to zoom in on the scope, and I'll do it off. So there it is with the capacitor in place, right? We see a straight line here. I'll just, oh, that's the trigger, in the wrong mode. Actually, let's just leave it the way it is. So we've got no frequency, we've got DC, it looks nice, and we have an average, an RMS voltage of 11 point whatever volts, and we have a V top of 11.6 volts. So that's just the peak that it's found. There's probably still some ripple on that, but watch what happens when you take the capacitor out. Right? And I'll put the capacitor back in. So the capacitor is smoothing the output of the rectifier. So what we have here, if you looked at my earlier video of trying to build a regulator for a regulated power supply for a charging circuit, I'll link that below, is we have what was in the unregulated power supply for that circuit. Because what happens on this is that if we were to put a load on it, the voltage will go down. Let me think about what I might have as a load, and I'll come back and we can try that. So I think I found something to use as a load. These are just two 100 ohm half watt resistors that are stuck together. So that's 200 ohms. I don't know what the load will be. I haven't figured it out, but 50 milliamps maybe. It's going to be close to the rating of the half watt resistors anyway. So we'll just do this briefly. But what we want to do is watch. So keep in mind what this looks like on the scope is that we see a straight line that's being filtered by that. And the voltage is staying up around 11 volt, around 10.5, 11 volts. If we go into the multimeter, which is set on DC, it shows that as 10.25 volts, and it's pretty well rock steady. So let's see what happens when we put a load on it. So do you see that? As soon as you put a load on it, it tends to go down in terms of voltage to the 6 volts that the power supply is rated for. Actually, those aren't heating up too badly. So 11 volts, right? Put the load on it, it goes down to 7.25, right? We'll build this as a 6 voltish power supply, I think. There's a little heat in those resistors, right? So we're putting some load on it. Now, of course, we could measure that load. If we wanted, we could look at the amperage across two. So I'll just write down on my notes here. So that's 200 ohms. And let's do it this way. Let's put the scope on. I'll put it on amp. Let's put it on amps. Make sure everything's unplugged before we do that. And what I'll do is get another black lead so we know what's going on. We'll put with that one there. And we'll clip that on here. And now we'll see, we'll go into DC amps. So one of the nice things about the Handtech, we'll zoom in. Oh, we're getting flare reflection again. Okay, we'll zoom in a little bit. One of the nicer things about the Handtechs is it tells you what to plug in. So let's connect this up and let's see how many amps is being drawn. So 22 milliamps, right? And 22 milliamps drops the voltage, or we can look at that by going back into the scope, right? So 22 amps drops the voltage from, why are we not seeing that? Oh, we're not seeing it because these don't work when, all right. But we saw it before anyway. Yeah, so the relay has opened so that the when you're out of the multimeter mode, they don't function. But we can see that. We can see that we've got, so 22 ohms, it draws, oh, maybe a little bit more as I'm making, so it draws 33 milliamps. So that's interesting. So we can see what happens when you load down the power supply, is that the voltage drops down, and only 33 milliamps is sufficient to do it. And we get that gets the voltage down. Let's put it back in DC volts. Get rid of that. We'll hook in. Yeah, that's the positive. These cheap alligator clips are not very good, so I'm hooked back into the positive here. We're out of the ammeter mode, and just to remind us how much the voltage drop is, so it goes down to drops to 7.75 volts. I'm just writing it out of frame. We'll call it 0.75. It's bouncing around a bit, and that's probably bouncing around with my things moving around on the cheap breadboard, and possibly also my line current changing. And we'll say from 11 volts. Okay? All right. So this creates a problem if you're trying to use this sort of thing with any sort of electronic device, in that unless it's something fairly forgiving, like, say, a transistor radio, you're going to want a regulated power supply, one that maintains the voltage. And that voltage, jump, right, between loaded at 7.75 to 11 volts, if you're trying to use it with 5 volt or 6 volt nominal semiconductors, you're going to blow them up. And that's a problem. So let's look at the next step. How would you create a regulated power supply from this? And the simple solution is, of course, to add a regulator. And a regulator is purpose-built semiconductor. This is an LM317. I don't know if that's going to focus for you. Probably not. And in the previous project, which I posted the other day, and I'll pull out the schematic I used for that, I built a regulated power supply based on an LM317, and that's what I want to do here for us today. So I will unplug everything, and then we'll build that circuit and see what happens. All right, so let me show you this schematic that I put together when I was working on the other power supply. So I used a regulator for that, an LM317, just like that. And that's got an in and an out. And there I had, ground is negative, plus is positive. There I had an unregulated power supply, but it was smoothed, and it did have, it was smooth, and it did have obviously a bridge rectifier in it. So in other words, it's this. We'll get this out since we're not using it. So in other words, the power supply that I had was entirely analogous to what we've got hooked up here. We have a rectifier, we have, pull it into the shot, we have a linear transformer, and everything is unplugged, I should say, and we had a smoothing capacitor on the output. So to make the LM317 work, it's an adjustable voltage. So it has two resistors, resistor 1, which is over here. There I used 240 because I wanted to set it for a fixed output voltage of 9 volts, which I eventually changed to 8.5 by modifying these numbers slightly. Here I'll just simplify it and use a 220 ohm resistor for there. And that's called R1. The second resistor then is R2, and there I used 1500 ohms. What I'm going to use for this one is, this is a 104, so this is a potentiometer, and I'm going to use a potentiometer in the range of R2, which will allow me to adjust the voltage. And my aim here is going to be for 6 volts regulated. And you can predict the output voltage with this equation, which comes from the data sheet for the regulator, which is 1.25 times 1 plus R2 over R1, and that sets how this, essentially this is a voltage divider that works to set the regulation point of the chip. So what I'm going to do is do the same thing, but this is going to be a potentiometer, and this is going to be 220. So if we draw that out, I'm going to do that right now. So here's our, so we'll run plus into here, and minus will make ground, right? So that's coming in. So plus is going to go to the in of the LM317. Out of that, we'll put on a smoothing capacitor, which will go to ground, and we're going to want to have plus 6 volts is what we're going to aim to do with this power supply. So then we have what's called the adjust pin. So this is in, and this is out. This is adjust. And there we put our voltage divider. So we'll put R1, which is going to be 220 ohms, right? And then that goes to there, and then we'll have our potentiometer. I'm sorry, that's terrible. Which will go, I think this is 104, so that means 10 and 1, 2, 3, 4 ohms. So that should give us, in other words, that's a 100K ohms potentiometer. That's not ideal, but that's what pulled out of the box. So that's what I'm going to use, and that should give us enough range if we're looking for, 15K. It'll be a bit down at the end, but it'll be all right. 103 would be too small, and I couldn't find any 203s, so that's what we got. So I'm going to assemble this circuit that I've doodled out here, and let's see if it works. Okay, much mucking around, and we now have a 6-volt regulated power supply. So R2 on here is around about 1,000 ohms, a little less, I think. I tried ballparking it with a 1,000 ohm resistor before I put the pot in, and the pot is a 203, so I did eventually find something that's a little bit more appropriate. So this pot is a 203, so 20,000 ohm range pot, which is about right. R1 is 220 ohms. Everything else is as you see. Here's the smoothing capacitor. There's the regulator, which is running nice and cool now that I've got it working properly. We have the regulator, which is taking, so I'll just show you what the voltages look like. So this is, I've now moved things around a bit. So the AC input comes into the rectifier over here. Here, let me zoom down a bit, and we'll start that over. So the AC off of the secondary of the transformer comes in on these 2 blue wires, and it comes into our diode rectifier here, made with 4 diodes. That then comes down to this bottom rail, which I'm using as the smoothed AC. So that comes onto those. That has a capacitor on it, which may or may not be necessary really, but it does help. That then goes, the negatives as the ground are tied together here by this wire. The positive goes into the input side of the LM317. The output of the LM317 goes to the negative rail on this side. So this is our regulated rail on the top. The output also goes to our resistor divider, so it comes out through a 220 ohm resistor. That goes into this pot, and it also comes out here to the adjust pin. So the adjust pin is monitoring the midpoint between that, and then the wiper of the pot is going to negative. Right, so that's operating as a resistor divider, and you can adjust the voltage by adjusting the pot. So that, if we come back to this equation here that describes the behavior of the regulator, the voltage output, we are adjusting R2, and as we move R2 up, the voltage will go up. Right, as we move R2 down, the voltage will go down. And to get 6 volts, we need a little under, about 900 to 1,000 ohms. So if you look at the voltage over here, let's see if I can get this in shot without it. You can sort of see that. And yes, I did need the calculator to figure this all out. You can sort of, it picks up the light. So we can adjust this potentiometer, and as we move it around, the voltage changes. I'll keep it. All these things are very fiddly. Anyway, we'll leave it at that. That's 6 volts as far as I'm concerned. Now the other thing that we could look at is we can compare that voltage to the voltage we have on the other side of the rectifier. And on the other side of the rectifier, we're seeing, you know, that 9 volts or so, 9.5 volts that we were seeing before, right? So let's put a load on it. And, well, let's do one thing first, okay? So let's put, let's have a look with the scope. So that's looking at the output here, and we've got nice, smooth, rectified DC at, you know, 6 volts, right? That's set for 5 volt increment. So it's sitting there right above the line. So 6 volts. Okay, so let's go back to the multimeter because that's going to be more interesting now. So let's put a load. So we'll undo these. We'll put this back on the line here, and let's put a load across the regulated output and see what happens. And these are the same 2 resistors I used before, so that's 200 ohms, and they drew 300 milliamps before. I don't think they'll draw as much at 6 volts, of course, so let's see. So I put them on, and the voltage goes down just 1/4 volt, right, and goes back up. So putting a load on the power supply reduces the voltage slightly, but not as much as you would think if you put it on the unregulated side. So let's have a look at what happens to the unregulated side when we put a load on the regulated side. I'll do the same thing. So I'm doing exactly the same thing as before. I'm just putting a load on the regulated side. And you'll see that the voltage on the unregulated side drops, but the regulated side only varied by 1/4 volt. But here it's dropping by, over 1.5 volts. Well, not quite 1.5 volts, right? But it's dropping from almost 10 volts to 8.3. So 0.7 volts results in a much less of a variation on the regulated side. And that's what a regulated power supply does. It produces the same voltage regardless of the load on the circuit. So let's just push the scope meter out of the way and just remind ourselves what the circuit is, right? And this is about the simplest possible circuit for this purpose that we could look at. This is essentially right out of the data sheet for the chip. There are a variety of improvements one could make to this, but that's beyond what we're trying to do here. Is just do the absolute most basic implementation of the regulator. Right? You can play with the capacitor ratings. If you were to put a pulse load on it, having a bigger capacitor on the output would be helpful. So at the moment I think this is 220, let's see, 220 micro, I think. I think that's what it is. 220 microfarads, and there's one on the input side as well. That's 220. So yeah. So you could put, like for an audio amplifier, you would put a big capacitor on the output side here to provide capacitance so that if you had pulsed load, like say driving a speaker, you wouldn't see it in the output. And there are a variety of other things. You could put inductors. There are a variety of kinds of filtering you can do because, of sure, this makes some noise. So I hope you've enjoyed this little look into me kind of exploring the simplest possible regulated power supply I could build. I think this kind of circuit could be useful in a lot of circumstances where you have an existing device with a problematic external power supply for some reason, or you want to deal with noise. I mean, obviously you can worry about the capacitors, but if you want to regulate it, you can. And if you replace, like I did in the earlier project, you can essentially replace the protection diode with one of these regulators. And if you do that, you get the protection of the diode because this looks like a diode, and you also get protection for overvoltage through the regulator as well. So it's not like a crazy modification to make of a lot of things, assuming that you won't, by doing so, drop the voltage so much that whatever you're working on won't work. Well, I hope you've enjoyed this little video, and thanks for watching.